Hello, and this is a presentation on automatic software test generation and the work that we've done in IIT Carlo as part of GameCore, our research center in software and computing. You have my details here, and this online presentation is also available at that URL there on the bottom left. So we're going to be looking at how do we can hope to generate software tests from source code, a variety of programming languages, and what the challenges are and how we've done work here in IIT Carlo to address those issues, which is all to do with software development and the maintenance of software. So first of all, what do we mean by automated software testing? The running of tests is generally easy. It requires a lot of work, but it's not unsurmountable. The difficulty is that it's extremely time consuming. We can use tools such as unit testing tools, C unit, J unit, etc. That is not the problem. It's actually the fundamental problem is actually unsolvable in that creating the test in the first place and writing the test in a way that we can call the various subcomponents of a piece of software and check the results that are expected is what is time consuming. The problem is unsolvable. It's similar to the halting problem in computer science. Research progress is slow, despite the fact that in real world, everybody has to test their own software before release and after release during maintenance. But a lot of it is still a manual process. Because in effect, to generate a particular test that's going to exercise the code in a specific way requires intelligence and understanding of the code. Yes, tools can help with that, but it's very easy to write code that tools cannot understand. Okay, it may seem paradoxical, but even a very basic programs can be very difficult for tools to actually analyze. Real applications in software development are endless. The current situation in industry at the moment is, of course, that it is expensive, slow, and it's not done very well, and hence a lot of software are released with bugs remaining, and the development process takes longer than it should. Than if we had actual automated software testing, which addresses the problem of generating the test in the first place. Running the test, checking the results, all of that is automated. Coming up with the tests themselves is still a manual process. So we can view software as a maze. And we basically have to try to explore that maze with all the if statement, the loops, the switch statements, whatever your programming language offers. Basically, you take a particular path through a program every time you exercise and every time you use a piece of software. Exhaustive software testing is impossible because there are too many paths available. There's hundreds or millions of ways, typically even in the most basic software package, in which a software can be exercised. And even if you take a particular path, it might work one day, but not the next, because the data that you use to go through that particular path is different. Okay, maybe the bug can only be exercised when you have a specific input that say generates a division by 0 somewhere in that particular path. So unless you've constructed your data, your test, exactly as it should, so that on that particular line where you've got that division, you're going to get your runtime error, then you will not find the bug. We have bugs that are illustrated here in a darker color to illustrate that every time you go through the path, you will find those bugs. Those are nice because they will always be revealed as soon as you go through the path. But other ones are a bit more harder to find because you might go through that particular path, or maybe a number of paths that go through this particular area of the code and not find the bug because you haven't exercised that particular path or that subset of path with the right data. Okay. We cannot exercise all the paths and we cannot exercise all the input universe of the tool. So we need analysis of the code so that we can try to fully as we can explore this maze, but it is difficult and it is not 100% guaranteed. Software testing cannot guarantee correctness. This is a well-known fact. So how do we explore this code maze intelligently and as efficiently as we can make it? The technique that we used here is based on symbolic execution, which is an old static analysis technique from the 70s. But we guide it with constraint solving because it's not a pure mechanical process. We need to check that the path we're currently following will actually lead to something that we want to add to our set of tests. We need to find this particular input that will make this denominator in a division to become 0, so that when you actually run the test, you will have an exception or a runtime error being raised. So constraint solving is there to guide the symbolic execution, as well as other heuristics based on graphs, basically, typically. So symbolic executions, mid-70s technique. It's a static software analysis technique that allows us to generate tests as well as other things, but that's mostly what we're interested in here is generating tests. In symbolic execution, actual values such as 3 are not used, but instead symbolic values, for example, x, are used. Okay, so normal execution obviously use actual data, but in symbolic execution, we keep our variable to be x, y, and if we have an x plus 2, well, we keep it as x plus 2. And then if we want x plus 2 to be equal to 0, then we use a constraint solver to say, well, x plus 2 equals 0, so therefore x should be minus 2. And that is one constraint that has been solved on that particular path. Of course, it's a bit more complex than just x plus 2 equals 0. So the constraints can be quite complex. And of course, the path can be extremely long in terms of hundreds of thousands of instructions. So we can build testing tool based on symbolic execution. And what we end up with is kind of a meta compiler. Okay, because it's not really a compiler and it's not really an execution. It keeps it everything abstract or symbolic. Okay, it's very powerful in theory because in theory it's a mathematical representation of the entire behavior of that particular piece of code for all paths, for all data. But in practice, there's a lot of problems. Okay, some problems are listed on the right hand side here. We have if statements. When we have an if statement, we have a fork in the path of execution. So which fork do we follow? Do we go to the true branch or the false branch? Well, it depends on the heuristic you're applying. And then what happens if you're following a particular branch, but then you find out that it doesn't lead anywhere afterwards, or the path is actually impossible? So in that fact, you typically have to backtrack or find another way of going where you want to go. Okay, loops are difficult because they create many more paths, and library calls to external entities or external pieces of behaviors are difficult because the source code is not available. Okay, we base symbolic execution on the source code. If we make a library call or an operating system call or anything external, we don't have the code for that. So the tool is basically doesn't know what to do. So those are our problems. On the side of the constraint solver, we use constraint logic programming, which is a much more recent development. We explore the maze at will using a dedicated constraint solver to guide the search. It's purely logic-based. We use a graph of the maze using pre-analysis stage to guide the search so that we don't have to go into areas of the graph of the maze that already been explored, for example. We're able to decide between true, false branch and constraint symbolic values accordingly so that we can focus on part of the maze that haven't been explored yet. We need to detect, we can detect infeasible paths, which are dead ends, and turn back, or we could say backtrack without having to redo the entire analysis, okay? Because the analysis is quite complex and quite expensive in terms of runtime. So, you know, if you follow the 10,000 instructions and the last one makes your path impossible, or you can't go to the last bit of the if that you want to, you don't want to start from the start again. You want to just undo the latest step that you've done. Okay, so a number of strategies based on that we've developed. All of that is based on using Prolog, the programming language based on manipulation of symbols. So it's highly suitable for symbolic execution because we'll use symbols such as X rather than actual values such as 3. So Prolog is well used for that, and also backtracking, turning back if you want, when we reach a dead end comes for free. We don't have to code that. It's part of the framework of the programming language, and that's also a great advantage of using Prolog. So in our nutshell, our unique approach to generating tests from source code is to use symbolic execution of source code using Prolog and a dedicated constraint solver for test data generation, search guiding, graph, and other heuristics added on to that to make the approach as feasible as possible. So the prototype tools that we've developed so far for a number of programming languages, we've done quite a bit of work for Ada, programming language highly suitable in avionics, where safety and correctness is more important than in others areas. It's important to note that Ada is coming back a little bit as well in embedded system and also in financial system due to its highly rigid structure. Done work on C and Java bytecode as well, which is interesting because bytecode is kind of an intermediary language that can be used for many other higher level languages. The problems that we've solved is to deal with conditionals, loops, function calls, pointers, etc. Pointers are listed in the literature as being problematic. We found a way of dealing with that. Basically, we do a memory map and we represent the memory and can put constraints on that. This is essential for a programming language such as C, for example, where pointers are absolutely everywhere. Important to note that we deal with function calls or procedure calls naturally. So, you know, as in a current execution, a normal execution, if you want. And so, you know, we can do quite deep analysis, and function calls are not a problem at all in the approach that we're using. Pending problems, the main one that we have is library calls, because we don't know the source code is not available. So the number of techniques there available that other people use that we need to adapt for our own work, and is to combine it with congruent execution. So in other words, if we have a method call, a function call that is for which we don't have the code, we can try some values, call the code that is external, gather the result, and then see if that fulfills the current constraint of the path that we have. If yes, we can carry on. If not, we might try a few random values to try to find something that is suitable for us. So we will be combining concrete and symbolic execution to deal with unseen or unavailable libraries. We've improved quite a lot our processing power and the amount of tests that we can generate quickly by 10 times over a number of years. The most developed tool is based on Ada, and here is a GitHub account where the tool has been open sourced. So you can see all the glory details of the parsing, and the constraint solver is all there, and as well as the graph analysis and all of that. And the tool is fully functional, and I invite you to use it. Implemented applications, in other words, what we can use our tools for, principally is to 4 areas: improving code coverage to complete test suites automatically. So for a number of coverage decisions, or criteria, if you want, branch coverage, decision coverage, and as well as MCDC coverage, which is used in avionics. Okay, so that depends on how thoroughly do you want to explore the maze if you want. We can also use to raise the coverage. Let's say you have a set of tests that is not complete, but it already exists, and you want to keep those, but you want to augment the coverage. We can do that, and we, for example, raise the coverage from your current test suite from 80% to 95% by adding the test that covers more of the code than the original test suite. Generating highly adequate regression test suites automatically for legacy software. Legacy software is often defined as software without test. And there's quite a lot of software out there which have no test actually been written available for it, which obviously for code maintenance is problematic, because you run the risk of breaking something that used to work, but you won't know it because you cannot test it because you have no test. Of course, you can generate the test manually if you want, by hand, but you're talking days, weeks, months in order to generate adequate regression test suites by hand. Our tool can generate regression test suites in minutes. Generating tests that raises exceptions. Here's a test that will raise an exception in your code at this particular line. And if you don't believe us, just go and run your code with that input and it will raise an exception. So we are targeting, micro-targeting our test to highlight something of value in the code that is problematic. And also for developers, we have a new technique called code querying, where the developer can query their own code and ask questions. Is it possible for this variable to have this value at this line? Give me a test input that will reach this line in the code satisfying this condition. And we have adapted our search to answer those kind of queries. And embedded into an IDE environment, it becomes a very powerful tool to think about your own code. So those are the range of things that are quite mature and that we managed to implement, especially for Ada. Here is the Ada version. It's called Mika, and okay, we won't go through that all, but different versions of Ada, switches, etc. The code coverage strategy that is wanted. At what depth do you want this? And here is some example code on the right-hand side. So we have an IDE. You can obviously use the command line tool to integrate that in as part of your tool chain. What I want to do now is to shift towards more applied research, is to develop in an agile way practical software development tools for developers. So that would require probably a change of emphasis from Ada, let's say, to C or a similar language, and also to tackle the problems of library code from day one, okay, as early as possible. Okay, so as part of a minimal viable product, the idea is to start with quite a small target, but something that is already kind of complete, and develop this, learn from it, and then only then enlarge the subset of the programming language targeted progressively. Okay, it's a big problem, so it's not something that's going to be done very, very quickly. There's a lot of work involved. If you look at the source code as available on GitHub for Ada, it's a big piece of work. It's like, as I mentioned, writing on compiler, except it's a meta compiler, so it's it's a big piece of work here. I'm looking to share, or we're looking to share our work with companies with C or maybe Java code or any others really. It depends what level of involvement you want. For software development, in particular, automatic test suite generation to achieve higher code coverage, triggering runtime errors, as we mentioned, and then code querying as well as part of an IDE. For software maintenance, automatic regression testing, allowing us to check the behavior of a new version of the code compared to the other one with a test suite that is highly complete that when you think of your maze, you have achieved a high level of coverage of the existing behavior. So it increases your confidence that the changes that you've made have not broken anything that used to work, and that the new parts that you've written also behave as you expected. In terms of researchers and students, we're looking at students interested in practical tools, static code analysis, which is growing in software development, obviously software testing, parsing code, constraint solvers based on Prolog programming. Okay. I thank you very much. This is the name of the address of my website where you can find me and more information. Thank you.